February 15, 1943. The Sahara Desert outside Sidi Bou Zid, Tunisia. Staff Sergeant Robert Mitchell of the 701st Tank Destroyer Battalion crouched behind a sand dune, his field glasses trained on something that shouldn't exist. Less than 500 yards away, a massive German tank sat motionless in the desert, its angular turret pointing skyward at an unnatural angle. Smoke drifted from its engine compartment, but the machine remained intact. This was no ordinary Panzer III or Panzer IV that American forces had grown accustomed to engaging. This was something entirely different, something that would fundamentally change everything American engineers thought they knew about armored warfare. The beast bore the number 250031 painted in white Gothic script across its turret rear. Its hull stretched nearly 21 feet from nose to tail, dwarfing the abandoned Sherman tank that lay burning 200 meters to its left. Even disabled and silent, the German machine radiated an aura of mechanical menace that made Mitchell's hands tremble as he adjusted his binoculars. The morning sun glinted off armor plates that seemed impossibly thick, casting sharp shadows that emphasized the tank's brutal geometry. This was humanity's first encounter with the Panzerkampfwagen 6 AOSF. The Tiger. Captain James Bradley received the radio call at 0800 hours. Recovery teams were needed immediately for what intelligence officers were calling a Priority 1 intelligence asset. Bradley had overseen dozens of battlefield recoveries during the North African campaign, but something in the radio operator's voice suggested this mission carried unusual significance. Within 2 hours, Bradley's heavy recovery unit was racing across the desert toward coordinates that would place them dangerously close to German positions. The recovery operation required 3 M4 tank retrievers working in coordination to extract the Tiger from its sandy resting place. The German tank had suffered a catastrophic transmission failure during the previous day's engagement, leaving it immobilized but structurally intact. American forces had waited until nightfall to approach, expecting booby traps or demolition charges that never materialized. German crews had apparently abandoned the vehicle in haste, leaving behind technical manuals, spare parts, and most importantly, a complete example of Germany's newest heavy tank. Loading the Tiger onto transport equipment proved nearly impossible using standard American recovery gear. The tank weighed 56.9 tons, almost twice the weight of a Sherman, and exceeded the capacity of most Allied transport vehicles. Engineers had to construct reinforced loading ramps and employ multiple recovery vehicles to move the machine onto a specially modified railroad car. Even experienced recovery crews who had handled hundreds of disabled tanks stood in silent amazement at the sheer mass and complexity of the German design. March 8, 1943. Aberdeen Proving Ground, Maryland. Colonel William Barnes, Chief of Ordnance Development, watched as Tiger 250031 rolled off its transport car onto American soil. The journey across the Atlantic had required special shipping arrangements and diplomatic coordination with British allies who wanted their own examination opportunity. Now, for the first time in history, American engineers would have unrestricted access to Germany's most advanced armored fighting vehicle. The Tiger's arrival at Aberdeen created immediate excitement throughout the Proving Ground's technical staff. Engineers, metallurgists, ballistics experts, and automotive specialists gathered around the machine like archaeologists examining an artifact from an advanced civilization. Initial visual inspection revealed construction methods and engineering approaches that contradicted everything American tank designers believed about armored vehicle development. Major Robert Honeycutt, Aberdeen's senior automotive engineer, conducted the first detailed examination of the Tiger's power plant and transmission systems. What he discovered challenged fundamental assumptions about tank design philosophy. The Tiger employed a Maybach HL230 P45 engine producing 700 horsepower, nearly twice the output of the Continental R975 engine powering American Sherman tanks. The transmission system featured 8 forward gears plus 4 reverse gears, providing unprecedented flexibility for a vehicle of such enormous weight. The engineering precision became apparent immediately upon opening the Tiger's engine compartment. Every component showed machine tolerances measured in thousandths of inches. Gear teeth exhibited perfect spacing and finish quality exceeding automotive industry standards. Electrical connections employed waterproof connectors and systematically organized wiring harnesses that suggested manufacturing by precision instrument makers rather than tank builders. American engineers noted that individual components appeared overbuilt for their intended function, designed with safety margins that seemed excessive by American wartime production standards. Captain Edward Morrison, Aberdeen's gunnery specialist, focused his attention on the Tiger's primary armament, the 88mm KWK-36L/56 gun, represented a scaled-up version of Germany's feared 88mm anti-aircraft gun, adapted specifically for tank warfare. The weapon's barrel measured over 16 feet in length and weighed nearly 3 tons. Examination of the gun's construction revealed manufacturing techniques and metallurgical processes that American ordnance plants had never attempted at production scale. The gun's recoil system employed hydraulic mechanisms of extraordinary complexity. German engineers had designed the system to absorb tremendous firing stresses while maintaining accuracy for rapid follow-up shots. The elevation and traverse mechanisms operated with mechanical precision that reminded observers of Swiss watchmaking rather than military equipment. Optical sighting systems bore Zeiss markings and provided magnification and clarity superior to anything in American service. Test firing of captured ammunition demonstrated effective ranges exceeding 2,000 meters against armored targets. Ballistic testing against the Tiger's armor began on March 15, 1943. American engineers positioned the tank at Aberdeen's primary testing range and systematically fired various armor-piercing projectiles against different sections of its protective plating. Standard 75mm armor-piercing rounds fired from captured German anti-tank guns bounced harmlessly off the Tiger's frontal armor, leaving only scratches on the hardened steel surface. Even 76mm high-velocity rounds struggled to penetrate the tank's side armor at combat ranges. The Tiger's armor protection system revealed sophisticated engineering that went far beyond simple thickness measurements. Frontal armor measured 100 millimeters thick, nearly twice the protection of contemporary American designs. But thickness alone did not explain the armor's effectiveness. German metallurgists had developed steel alloys and heat treatment processes that produced armor plates of exceptional hardness and resilience. Face-hardened armor employed different steel compositions on the surface versus the backing layers, optimizing protection against specific types of projectiles. Examination of the Tiger's running gear and suspension systems provided additional evidence of German engineering sophistication. The tank employed torsion bar suspension with overlapping road wheel arrangements that distributed the vehicle's enormous weight across a broader ground contact area. Each road wheel station featured individual torsion bars calibrated to provide optimal ride characteristics and mechanical reliability. The track system employed individual steel links weighing over 20 pounds each, connected by hardened steel pins that required special tools for removal. Interior examination revealed cramped but efficiently organized crew compartments. Despite the Tiger's external dimensions, internal space remained limited due to the thickness of armor protection and the size of mechanical systems. German designers had maximized the use of available space through careful component placement and ergonomic considerations. Control systems featured precision-machined levers and switches that operated with mechanical precision. Radio equipment, electrical systems, and instrumentation appeared to be manufactured to higher standards than comparable American military electronics. The Tiger's complexity became most apparent during maintenance and repair exercises. American mechanics attempting routine service procedures discovered that virtually every operation required specialized tools and extensive technical knowledge. Oil changes demanded removal of multiple access panels, secured with unusual fasteners. Track maintenance required hydraulic equipment to handle the enormous weight of individual track segments. Engine service procedures involved complex sequences of component removal that would be impossible under field conditions without factory-level facilities and trained specialists. By April 1943, Aberdeen's technical staff had compiled comprehensive reports documenting every aspect of the Tiger's design, construction, and performance characteristics. The conclusions reached by American engineers would fundamentally influence American tank development for the remainder of the war and beyond. The Tiger represented engineering excellence that American industry could not match, but also revealed manufacturing approaches that American mass production philosophy would never accept. The German tank embodied precision craftsmanship applied to military hardware with an attention to detail that seemed almost obsessive by American standards. Every component showed evidence of individual attention during manufacturing. Tolerances exceeded functional requirements by significant margins. Materials employed costly alloys and specialized treatments that added manufacturing time and expense without proportional increases in combat effectiveness. The Tiger was undeniably superior to American tanks in firepower, protection, and mechanical sophistication. But it was also a machine that only German industry could produce, and only German logistics could sustain. Colonel William Barnes walked slowly around the Tiger, his engineer's eye cataloging details that challenged every assumption American tank designers had made about armored warfare. The precision of German manufacturing became more apparent with each inspection. Weld seams showed uniformity that American production lines achieved only under laboratory conditions. Paint application appeared flawless despite the vehicle's combat history. Even battle damage revealed the quality of underlying construction, with armor plates maintaining structural integrity despite impacts that would have shattered lesser materials. The transmission became the focus of intense scrutiny during the following weeks. German engineers had designed a system of extraordinary complexity, featuring planetary gear sets and sophisticated clutch mechanisms that enabled precise control of the massive vehicle. American automotive engineers familiar with commercial truck transmissions found themselves studying components that seemed more appropriate for precision machinery than military equipment. Each gear displayed machining tolerances measured in fractions of thousandths of inches. Bearing surfaces showed polishing quality exceeding aircraft engine standards. Major Honeycutt supervised the complete disassembly of the Tiger's final drive systems. What his team discovered revolutionized American understanding of heavy vehicle engineering. The final drives employed epicyclic gear trains with multiple reduction stages, each manufactured to tolerances that American mass production facilities could not achieve reliably. Individual gear teeth showed uniform surface finishes achieved through specialized grinding processes. Housing castings displayed internal geometries requiring precision boring equipment that few American factories possessed. Testing of the Tiger's electrical systems revealed another dimension of German engineering sophistication. Circuit protection employed fuses and breakers designed specifically for armored vehicle applications. Wiring harnesses used insulation materials resistant to vibration, moisture, and temperature extremes. Junction boxes featured waterproof sealing systems that maintained electrical integrity under conditions that would disable American equipment. Radio equipment included vacuum tubes manufactured to specifications exceeding commercial broadcasting standards. The Tiger's hydraulic systems demonstrated engineering principles that American designers had never applied to military vehicles. Turret traverse mechanisms employed variable displacement pumps controlled by precision valves. Hydraulic lines featured pressure ratings far exceeding operational requirements, with safety margins that seemed excessive by American production standards. Filtration systems included multiple stages designed to maintain hydraulic fluid purity under extreme operating conditions. Every hydraulic component bore inspection stamps and serial numbers indicating individual testing during manufacturing. Ammunition storage and handling systems within the Tiger revealed careful attention to crew safety and operational efficiency. Shell storage racks employed spring-loaded mechanisms that secured projectiles during violent maneuvering while enabling rapid access during combat. Propellant charge containers featured moisture-resistant sealing systems protecting explosive materials under adverse conditions. The ammunition handling system included mechanical aids reducing crew fatigue during sustained combat operations. Safety interlocks prevented accidental firing during loading sequences. Metallurgical analysis of armor samples provided the most shocking discoveries. German steel showed carbon content and alloy compositions that American mills had never attempted at production scale. Heat treatment processes produced hardness gradients optimized for different threat types. Surface hardening created extremely tough outer layers while maintaining ductile backing material that prevented catastrophic failure. Microscopic examination revealed grain structures indicating sophisticated temperature control during forging operations. The Tiger's optical systems established new benchmarks for military equipment quality. Periscopes employed Zeiss lenses ground to tolerances exceeding surveying instrument requirements. Gun sights featured reticle patterns etched with precision that required specialized equipment to measure accurately. Range-finding mechanisms operated with mechanical precision reminiscent of laboratory instruments. Prism assemblies showed optical coatings that enhanced light transmission while reducing glare under battlefield conditions. Engine analysis revealed the Maybach HL230 as a masterpiece of automotive engineering adapted for military service. Cylinder blocks showed precision boring achieved through specialized honing processes. Connecting rods featured weight matching within gram tolerances across all 12 cylinders. Crankshaft balancing exceeded standards for racing engines. Valve train components displayed surface finishes requiring specialized grinding equipment. The engine represented precision manufacturing applied to military hardware without regard for production cost or time constraints. Cooling system examination demonstrated German attention to thermal management under extreme operating conditions. Radiator construction employed materials and manufacturing techniques exceeding commercial automotive standards. Fan systems included variable speed controls responding to engine temperature and combat conditions. Coolant circulation employed multiple pumps, ensuring adequate flow under any operational scenario. Temperature monitoring systems provided crew warnings before critical component damage occurred. The Tiger's track and suspension systems revealed engineering solutions to weight distribution problems that American designers had never successfully addressed. Torsion bar springs employed special steel alloys heat-treated to precise specifications. Road wheel assemblies featured precision bearings manufactured to aircraft industry standards. Track pins used hardened steel, requiring special tools for maintenance operations. Rubber components employed compounds resistant to petroleum products and extreme temperatures. Fuel system complexity exceeded anything American engineers had encountered in military vehicles. Multiple fuel tanks featured interconnected plumbing with automatic switching valves. Fuel pumps included redundant systems preventing engine shutdown during combat maneuvering. Filtration systems employed multiple stages removing water and contaminants that would disable American engines. Fuel quantity indicators provided accurate readings despite vehicle attitude changes during combat operations. Interior ergonomics demonstrated careful consideration of crew efficiency during extended combat operations. Control layouts positioned frequently used switches within easy reach of crew positions. Seating systems provided adjustment ranges accommodating different crew member sizes. Vision systems gave commanders comprehensive battlefield awareness through multiple periscopes and observation devices. Communication equipment enabled coordination between crew members despite engine noise and combat sounds. Maintenance accessibility revealed the Tiger's most significant operational limitation. Routine service procedures required removal of multiple components using specialized tools. Oil changes demanded extensive preparation and equipment not available to field maintenance units. Track replacement required hydraulic equipment weighing more than entire American maintenance kits. Component access required technical knowledge exceeding the capabilities of typical tank crews. By May 1943, American engineers had completed comprehensive testing that would influence tank development for decades. The Tiger demonstrated that German industry could produce armored vehicles of unprecedented sophistication, but also revealed the limitations of such an approach. Manufacturing complexity made maintenance rapid production impossible. Requirements exceeded field capabilities. Resource consumption challenged even German industrial capacity. The Tiger represented engineering excellence that was ultimately self-defeating. The captured tank remained at Aberdeen through 1944, serving as a reference standard for American armor development programs. Engineers studying the Tiger's construction methods adapted selected principles to American production capabilities. Armor metallurgy improvements incorporated German heat treatment techniques modified for mass production. Transmission development programs applied German planetary gear concepts simplified for field maintenance. Gun sight systems adopted German optical principles manufactured using American production methods. General Omar Bradley visited Aberdeen in June 1943 to observe Tiger testing personally. His assessment proved prophetic for American armor doctrine development. The Tiger represented individual superiority that could not overcome numerical disadvantage. American production philosophy emphasized adequate performance produced in overwhelming quantities rather than exceptional performance produced in limited numbers. The Tiger taught American planners that technological superiority meant nothing without the industrial capacity to deploy it effectively. The psychological impact of the Tiger examination extended beyond technical considerations. American engineers gained profound respect for German technical capabilities, while simultaneously recognizing the strategic limitations of the German approach. The Tiger proved that precision engineering and manufacturing excellence could create superior individual weapons, but could not overcome the fundamental mathematics of industrial warfare. Quality impressed observers, but quantity would determine victory. Dr. James Morrison stood in the Tiger's turret basket, his head and shoulders protruding through the commander's cupola, studying instrument panels that seemed designed for precision instrument makers rather than battlefield commanders. The electrical systems employed waterproof connections and circuit protection that exceeded anything American military electronics achieved. Switchgear operated with mechanical precision that reminded Morrison of laboratory equipment. Even the radio installation featured vacuum tubes manufactured to specifications surpassing commercial broadcasting standards. The Morrison's primary focus turret traverse mechanism became during subsequent weeks of evaluation. German engineers had created a system of extraordinary mechanical sophistication that enabled precise gun laying despite the weapon's enormous weight. Hydraulic pumps maintained constant pressure regardless of engine RPM. Control valves provided infinitely variable traverse speeds from barely perceptible movement to maximum rotation rates. The entire system operated with mechanical precision that American tank designers had never attempted. Lieutenant Colonel Frank Stevens supervised ballistic testing that would determine American tactical doctrine for engaging German heavy armor. Aberdeen's primary testing range received extensive modifications to accommodate the Tiger's massive dimensions and the distances required for meaningful ballistic evaluation. Standard American anti-tank weapons would be tested against the Tiger's armor at various ranges and angles, providing definitive data on Allied capabilities against German heavy tanks. Initial testing employed the 37mm M3 anti-tank gun, standard equipment for American infantry units. Firing from 500 meters, the weapon's armor-piercing projectiles bounced harmlessly off the Tiger's frontal armor, leaving only superficial scratches on the hardened steel surface. Reducing the range to 200 meters produced identical results. Even at point-blank range, the 37mm rounds could not penetrate the Tiger's armor anywhere except perhaps the rear engine compartment under perfect conditions. Testing progressed to the 57mm M1 anti-tank gun, a weapon American forces considered adequate against most German armor. Results proved equally disappointing from American perspectives. Standard armor-piercing rounds fired from 1,000 meters failed to penetrate the Tiger's frontal protection. Reducing range to 500 meters produced marginal penetration of side armor under optimal conditions. Only flanking shots at ranges under 300 meters offered reliable penetration opportunities, tactical scenarios that battlefield conditions rarely provided. The 75mm M3 gun mounted in American M4 Sherman tanks represented the primary anti-tank weapon available to American armored units. Testing revealed the stark reality of American disadvantage in tank versus tank combat. Sherman's 75mm rounds could penetrate Tiger's side armor at ranges under 500 meters when striking at optimal angles. Frontal armor remained impervious to American 75mm projectiles at any practical combat range. The Tiger could engage and destroy Shermans at ranges exceeding 1,500 meters, while remaining invulnerable to return fire. Captain William Richards, Aberdeen's senior metallurgist, conducted microscopic analysis of Tiger armor samples that revealed German steel production capabilities far exceeding American achievements. Carbon content and alloy compositions created steel with hardness characteristics that American mills had never attempted at production scale. Heat treatment processes produced hardness gradients optimized for defeating specific projectile types. Surface layers achieved Rockwell hardness readings that American steel specifications had never required. The armor's construction methodology proved as impressive as its material composition. German manufacturers had developed welding techniques that maintained steel properties across joint areas. Armor plates showed uniform thickness maintained within tolerances measured in fractions of millimeters. Surface finish quality exceeded specifications for precision machinery components. Even battle damage revealed the exceptional quality of underlying construction, with armor plates maintaining structural integrity despite impacts that would have shattered lesser materials. Richards discovered that German armor employed multiple steel grades within individual plates. Face-hardened armor used different alloy compositions for surface layers versus backing materials. Surface steel achieved maximum hardness for defeating projectile tips. Backing steel maintained ductility, preventing catastrophic brittle failure. The combination created armor protection that exceeded the sum of its individual components through sophisticated metallurgical engineering. Optical equipment examination revealed another dimension of German technical superiority that challenged American understanding of military equipment standards. The Tiger's gun sight employed Zeiss lenses ground to tolerances exceeding surveying instrument requirements. Reticle patterns showed etching precision that required specialized equipment to measure accurately. Magnification systems provided target resolution that American tank sights could not match under any conditions. Major Robert Patterson, Aberdeen's optics specialist, spent weeks studying the Tiger's periscope systems. German manufacturers had created vision devices that provided exceptional clarity and light transmission characteristics. Prism assemblies employed optical coatings that enhanced performance while reducing glare under battlefield conditions. Mechanical adjustments operated with precision that reminded Patterson of astronomical telescope mechanisms rather than military equipment designed for combat abuse. The Tiger's range-finding equipment incorporated mechanical computing systems that automatically calculated firing solutions based on target distance and ammunition type. German engineers had created analog computers using precision-geared mechanisms that solved ballistic equations mechanically. American forces relied on manual calculations and crew experience for gunnery solutions. The German system eliminated human error while reducing crew workload during combat engagements. Engine compartment examination revealed the Maybach HL230 as possibly the most sophisticated automotive power plant American engineers had encountered. Cylinder block construction employed precision boring techniques that achieved surface finishes exceeding aircraft engine standards. Connecting rod manufacturing showed weight matching within gram tolerances across all 12 cylinders. Crankshaft balancing exceeded requirements for racing engines designed for maximum performance rather than reliability. The final reports compiled at Aberdeen Proving Ground in late 1943 would reshape American armored doctrine for the remainder of World War II and beyond. Tiger 250031 had taught American engineers a fundamental lesson about the nature of modern industrial warfare that no classroom or theoretical study could have provided. The German tank represented the pinnacle of precision engineering applied to military hardware, but it also revealed the strategic limitations of pursuing technological perfection without regard for mass production requirements. Colonel Barnes stood in the Aberdeen testing facility one final time, watching as technicians prepared the Tiger for long-term storage. The tank would remain at the proving ground as a reference standard, its components serving as benchmarks for American armor development programs. But the real value of the Tiger examination lay not in copying German methods, but in understanding why those methods could never determine the outcome of industrial warfare between major powers. American tank designers took specific lessons from the Tiger evaluation and applied them to future development programs. Armor metallurgy improvements incorporated German heat treatment techniques modified for mass production capabilities. The M26 Pershing heavy tank, rushed into development during 1943, employed thicker frontal armor and a more powerful 90mm gun directly influenced by Tiger specifications. Gun sight systems adopted German optical principles while using American manufacturing methods that enabled rapid production and field maintenance. But the most important lesson learned at Aberdeen had nothing to do with technical specifications or engineering details. The Tiger demonstrated that individual weapon superiority meant nothing without the industrial capacity to deploy it effectively. Germany could produce Tigers that outclassed American tanks in every measurable category, but German industry could not produce them in quantities sufficient to influence strategic outcomes. Each Tiger required over 300,000 man-hours to manufacture, compared to approximately 10,000 man-hours for a Sherman tank. American production philosophy emphasized adequate performance produced in overwhelming quantities rather than exceptional performance produced in limited numbers. This approach proved decisive as the war progressed. American factories delivered over 49,000 Sherman tanks to Allied forces by war's end, while German industry produced fewer than 1,400 Tigers, despite desperate need for heavy armor on multiple fronts. The mathematics of industrial attrition made German defeat inevitable regardless of individual weapon quality. The psychological impact of the Tiger examination extended far beyond technical considerations. American engineers gained profound respect for German capabilities, while simultaneously recognizing that engineering excellence without production capacity represented a strategic dead end. The Tiger proved that precision manufacturing could create superior individual weapons, but could not overcome the fundamental arithmetic of modern warfare. Quality impressed observers and influenced future designs, but quantity determined victory. Tiger II 50031 remained at Aberdeen Proving Ground through 1945, serving as a monument to engineering achievement and strategic miscalculation. American visitors studying the tank invariably came away with the same conclusion that had emerged from months of detailed analysis. The Tiger represented everything that German industry could achieve when cost and production time were secondary considerations. It also represented everything wrong with German strategic thinking during the world's first truly industrial war. In the end, the captured Tiger taught American planners the most important truth of modern warfare. Quality impresses, but quantity wins wars.